the lecture. This is the second day of our Digital Makers series, or like our lecture slam, as we like to call it, for this week, where we have three distinguished guests. Yesterday we heard Jonas Lundberg from Sweden, who talked about his work, and there was a lot of his work was shown also as a kind of academic work. And today we're very happy to have Jim Mendenhall here. Welcome, Jim, to Stuttgart, digital Stuttgart, you could say, where we basically, come together to find out more about digital making, digital design, and digital fabrication, and how to create this specific type of architecture that comes out of digital design. And we'd like to see how your company is realizing such work. Jim Mendenhall is working at Zahner in Kansas City, Missouri, and you're sitting there right now in this beautiful office. I can see the ceiling behind you, which is formed in a very specific way, and we also showed it already in our poster. We, makes us very curious to see, to hear about what you guys do as your main work. I mean, Jim, you Mendenhall is an engineer, studied in Kansas City, and after finishing his studies, he went to Zahner, I believe. I mean, first of all, I have to say, Kansas City is the same city that Jonas Lundberg was studying in yesterday, so everything is linked up in our series. Kansas City, you basically, after your studies, went into the company of Zahner as an engineer. You led the first 2 years, I believe, the company as project engineer, projects that you worked on. Then you moved on to project management. You met also, I guess, Simon from our institute in Hamburg, when you worked in projects in Hamburg. And then afterwards, you became in charge of the engineering department of Zahner, which you, I believe, are now heading. And Zahner is basically a company that realizes many of those complex geometric buildings that we see around the world. Many architects rely on you to realize their projects, and there's of course quite a bit of digital fabrication involved, and we're very curious to hear about it. I hear also that you're a multidisciplinary team. You're not just engineers, but you also have people working fine arts. So also that speaks of speciality that your company represents. So thank you for coming, Jim, and we're very curious to hear about your work. So the floor is yours.
Thank you very much for having me. It's a pleasure to be here, and to kind of follow up on Jonas's presentation yesterday, which was fantastic and very intriguing. I'm going to go ahead and share my screen and get this started. And can you all see that okay?
Yes.
Yeah.
Looks very good.
Okay, so I'll start off with a bit of an introduction to Zahner, the company that I work for. I've worked for the last 12, 13 years. Basically, we're an architectural metal fabricator. That's our specialty. And we've been in business for 125 years, so since 1897. Obviously, the business has evolved quite a bit over that time. We've really been pushing the digital fabrication side of things for really since the mid-90s. So what I'm going to start off by talking about is some of the projects that we've worked on over the years with different designers, kind of at a high level. And then second part of the presentation, I'll get into a deeper dive on a specific project SoFi Stadium in Los Angeles. HKS was the design architect on that. And then another project that a headquarters building for a company that I can't name at this stage, but it's a project that design architect was Heather Wick and the Archangels Group. So what you're seeing here on this first page is one of our fabrication spaces. These are some of our assembly crews putting together panels for the Peterson Automotive Museum in Los Angeles. And going to the next page, that is the completed Peterson Automotive Museum. Talking about digital fabrication, getting to a fabricatable product like this from the architect's original concept, there's a huge amount of work that goes into optimizing the geometry, the process, obviously working with structural engineers, structural requirements the entire time to achieve the architect's design intent. And really, at the end of the day, that's what we're here to do. The architect establishes the design intent for the building. We want to be, in Bill Zahner's, the owner of the company, his words, the hands of the artist. So we're going to provide the expertise on how to achieve their design intent. So this was a building, Cohn Peterson Fox is the design architect on this one, but quite a challenging one. And also being in Los Angeles, earthquake requirements are very stringent. And so structurally, this was a very challenging one for us, but the results are what they are. So talking about a couple other projects, kind of selected ones. This is the Cornell New York City campus, their tech campus on Roosevelt Island, just off the coast of Manhattan, or I believe it's in the Hudson River. So this one, Morphosis was the design architect on this project. And basically all the metal that you can see, that was all our scope. And zooming in on this facade, what you actually have is a series of perforations that we call louvered zera, this product, which is it's kind of a louvered perforation that is then turned by a robot to a specific angle to provide a specific texture to the building. So zooming out, and obviously a nighttime view, you don't pick up that texture quite as much from this photograph, but up close, adds a very, very unique texture to this building. And this is one of the products that we've developed pretty recently, still kind of optimizing that process, but we can start actually with an image, convert it to perforations, and then convert those perforations to louvers that are pushed at a specific angle to create a specific image or a specific, in this case, kind of a texture. This building is in Miami Design District, obviously in Miami, Florida, USA. It's a parking garage. And this was an interesting one, quite a challenge that we did a few years ago, that there's actually 5 different designers. So if you note, as the building, you go around this kind of curved portion, there's different facades, like almost completely different going down the building to the right. Basically, in this case, we had to work with each designer to figure out how to make their vision a reality using largely metal, although we actually had some milled polyethylene sheet in for this this scope right here. But really, in these cases, we're looking to break things up into a kind of panelized sections that can then be fabricated and installed in the field on the building with minimal tweaking needed to make the geometry. You can see some of the panelization in this closest section where these are some of the panel sections that are curved here. And we actually make this in a way that it's what we call a drop and lock system, where even with all these different types of facades, the attachment at the back is still a standard attachment method. So where there's a large aluminum extrusion, and we panelize the system for efficient transport from our fabrication facility to the project site. And then for installation, in theory, it can be very smooth because the installers are really just dealing with a standard attachment method on the back of the panel. All the complexity of the panel is built in the shop, where we can control within our facility a lot better the accuracy of that than could be done in the field. This project is Art Gallery of Alberta. So this is in Edmonton, Canada. This is one where we had to create a very smooth curved ribbon here. Stainless steel is a material for the panels at the end, and we actually formed all the substructure for this as well. And that's something that I'll get into with the deeper dives on two of our projects on kind of how we go about creating that substructure, optimizing that substructure to be able to form the often dual curved surfaces that the architect wants to see. This one is Emerson College in Los Angeles. Also Morphosis, the design architect on this project. We actually did a lot of different scopes on this project. The one I wanted to draw attention to is this, what we call a scrim wall that is inside of here that gives this really unique texture to that wall that is actually a flat wall, but because the panels, each panel in there is folded in a specific and unique way and then laid out over the wall. This is actually done, we worked closely with Morphosis on this. They obviously did the layout of what the panels, what pattern they wanted to see. And we worked with them on how to achieve that, in a way that is reasonably achievable. And they can translate to the field, be installed without too much, again, field adjustment being required. And this picture is really good, capturing some of the light from the sunset, kind of sweeping along those panels. This is a project called the Chrysalis. It's actually a bandstand, so it's for concerts. It's in kind of outside of Baltimore, Maryland, in the U.S. Mark Fornes was the designer on this one, and he's really more of an artist, not an architect. So you can almost think of this as a very large sculpture. We owned all aspects of this, so above the concrete. So concrete was another subcontractor, but we owned the steel substructure, aluminum substructure, and then these are actually aluminum skins painted different shades of green to kind of give a very organic look to this building where, you step back, it's in a forest. It really disappears into the forest, which is the intent of this. This was a building we did quite a while ago for Gary Partners. This is the Fisher Center at Bard College. Stainless steel, again, skins. And again, we had to form a substructure that achieved these very curvaceous organic lines, the flowing lines to the building, but still obviously could support some relatively large cantilevers and also have a nice sharp edge. So a lot of times the architect is asking for, a very sharp, clean edge, which can be very challenging to achieve, especially with a large canopy like this. But that's something we've gotten quite good at trying to define that in a way that can support the edge, but also provide a nice, clean, sharp, continuous edge that really catches your eye. This is a project in Honolulu, Hawaii. It's actually a parking garage, though it doesn't look like that, which is kind of the point. So it's called a Waiea garage, and this is actually using our what we call our image wall system, where we start with an image from the architect or the designer, and we convert that image into a perforation pattern. In this case, it's perforations and bumps, which I'll show on the next slide, kind of a zoomed in view on this. This image it's kind of abstract, but this is actually water on the beach. So kind of where the water comes in, a wave comes in and then naturally recedes, kind of what the sand looks like on that beach. So it's meant to be somewhat abstract, but still, once you kind of see what it's going for, it really pops out. And zooming in on these panels, you can see it's actually a series of different perforations and bumps. So both of these can be done in our punch machine that are meant to, we have a grasshopper program built out that converts the images to, again, perforations and bumps and achieves this. And the next, one thing that's interesting, I noticed when I was putting this presentation together, is there's a lot of what we do is stainless steel or anodized aluminum, which are gray metallic tones. We do a lot of non-gray tones too, though. So I wanted to show a project. This is in Jakarta, Indonesia. This is the Australian embassy. And so all these buildings were actually done clad in Zahner metal. And what we have here is zinc on this, basically starting from the left. We have a pre-patinaed zinc. The one in the middle going from left to right is more of it's a pre-weathered zinc, but not really with any specific patina coloration to it. This is actually a weathering steel, sometimes called core 10 steel. So it's a copper bearing steel that then we pre-weather to that stable rust color, and it will actually stabilize there for a very long period of time. So, and then this is also zinc. This is also zinc, and then this is actually pre-patinated copper. So obviously that's a reasonably common product, but taking the copper to that nice final green tone that it will get after decades of exposure naturally, we're able to get it there much quicker. This is actually what we call our star blue copper product. And some of the modeling you see, the different tones, is by design. We're not trying to achieve a paint-like consistent tone. It's more of an organic, natural range of tones that then will continue to evolve over time based on local weather patterns. This project is in Mexico City. It's for a department store actually called Liverpool by Roquín de Arquitectos. And this was actually an extremely challenging project where the architect and the owner came to us with 1 year to turn this around from basically basic design all the way to installation. So they had an opening date, which was almost exactly 1 year from when they approached Zahner. We were able to achieve that. One thing that's notable on this project, this is stainless steel panels that you see. I believe there were 7,000 skins on this project. We also created all the substructure. So to make that shape, underneath this building is actually just cylindrical. So the walls of the interior of the building are basically a cylinder. So we built out aluminum substructure to form the shape that then our stainless steel skins can mount onto. So an interesting thing with this project is there's a very good relationship between the owner, the architect, Zahner as the primary metal contractor, and the structural steel, the kind of building engineer. We had a very close relationship on this project, and that was the only way we were able to achieve this in under a year. Any sort of what I'll call some of the bureaucracy you can sometimes run into with different design dynamics can really slow things down, and there's some good reasons for that in some cases, but in this case, it really proved out that close relationship, that close kind of multidisciplinary relationship between designer, owner, fabricator, installer, and building engineer allowed us to really achieve something special. And so that's basically the end of the first part, just running through some Zahner projects to give an idea, high level overview of some of the work that we do. So leaving it there for a moment, we could potentially open up to questions.
Yes, I mean, thank you. I mean, we just for the audience who's hasn't been joining yesterday, we're doing 3 brief small lectures, and then in between we're going to have a moment where we can discuss what we just saw, because we think it's always missing in these long lectures, that we had a chance to talk about what we just see. So, I mean, I'm very curious about your work, because you're I mean, producing obviously the designs of these various architects, but I think it's also in a way very architectural. I mean, that you have to think, and I mean, there's also, I heard you're using similar tools that architects are using as well, and and so I think there's that kind of a match. What I want to know is, like, what was the, because you talked about the history about the company, what is the first building that you used any parametric or digital tools on? Do you know that? Do you have a?
So it wasn't the very first building, but the one that really it kind of matured on using parametric tools was the Experience Music Project, the Gary building in Seattle. It's not, I don't recall what the current name of the building is. It's not that anymore, but that was a very, what was that?
Just a giggle.
It was a very organic form. So it was extremely, I mean, that's his style, and to create that substructure, because it's similar to what I've talked about on some of these projects, we had to build out from structural steel that was more standard, boxes, out to a really organic flowing shape, the substructure. We did that with, I believe we were using Pro Engineer at the time, so which is called Creo now. But it was we were using that software, and actually we were still using that up until to the time I started in 2007. And using it on, I believe, some old Silicon graphics computers back in 98, 99. This was before I was with the company, but that was the first project where it's something, there's really not a way to achieve that project without parametric modeling. If we needed to hand design each of the substructure elements for that project, it would have been years of work by hundreds of people just to draw what was needed. So you really had to use a software that could handle the parametrics and automate some of that process. So that's really the one where it became somewhat mature for us.
Jim, for some time you've been offering like interactive facade designing tools on your webpage, like this image wall, and
Yes.
so how's the response by architects? Do they do you get like many requests, or people use it?
We do, yes. Image wall is probably our most mature product that we offer, and there is a configurator available on our website where you can upload a photo. So going back a few steps to this project, you could upload a photo of a beach, in this case, sand on a beach, and actually manipulate some of the dimensions and some of the contrast of the photo on our website, and get to a close approximation of what you would actually, the product you would get. We do see a lot of traffic from architects on that.
Okay.
It's a stepping stone. It's not like you can just do that and then click order and we send you the product. It's kind of the start of the discussion.
Okay.
To tweak and manipulate the image and what the project needs, and then produce that product.
Because I think you're the first guys who really offer like this depth of design finalization, where you can really achieve like a complex structure, individual designed via a website. I think that made maybe like a changer for architects, that that like we don't design it anymore. You don't have to engineer it. It's done by like the smart algorithm in the background.
Well, and to your point on that, and I think a point that was made in the presentation yesterday on the multidisciplinary team, with that tool, we've built in our expertise on metals,
Yeah.
on forming metals, on thicknesses. We've already built in the structural calculations. So, with the maximum panel size, the panels can only span so much distance in a certain thickness. We've built all that expertise in so that as the designer, you can come in, interact with that, and there's not okay, I want the design to look like this, but then when actually the structural calculations are run, it has to change completely.
Okay.
We've already built that in.
And yeah, that's interesting because the relationship between the architect, let's say, and your company, I mean, I find curious because you digital fabric design and digital fabrication, we talked about it yesterday. There's a possibility that you can actually, as kind of architects and engineers, you can start to kind of feed into that process of producing and fabricating. And I just wonder, because you're coming from this side where you're actually realizing this work, has this like changed the relationship between you and the designers, in the sense that at the moment we're looking at a very clear distinction between this is design, and then there's the handover to the builders, and then this is the construction. And of course, there's also everything, the whole system is tailored towards this. We have a liability system, also like we have insurances and so forth. So it's tricky to kind of starting to dilute that border. But I find that when you talked about before how you work with architects and designers, and I'm just curious, what is that relationship, like the communication during the design process? Do you see any changes in comparison to a
Absolutely.
traditional? Yeah.
Yeah, and I'm not sure if this translates directly to some of the European, the way that it's formatted, but so we have design, bid, build projects, which would be the more traditional. A project is designed completely. There's construction drawings. It's bid out to different contractors, and then it's built. So design build, which is where we prefer to operate, we're getting involved in the design phase and really as a consultant. So if designer comes to us with a design, and we'll get involved under what we call a design assist contract, where we're
PCSA.
often contracted directly to an architect.
Yeah.
In that case.
Okay.
Mhm.
So
And then,
the architect basically asks you to join the team, and then is basically paying you to consult. Is this what you? I mean,
correct.
it's
Yes.
a very close relationship. Yeah.
Yes. And usually with those contracts, we're going to try to get to a mock-up. So we'll build a physical sample of the thing that we're trying to get to make sure, that always helps, especially when you get to ownership groups, get final approval for that. And then we're also getting to a price that we can build it for. So, and it's not meant to be an advantage to us necessarily. It's an advantage to everyone. So it's trying to optimize that design to something that is feasible. So fits in an owner's budget, fits with the architect's design intent, and is fabricatable.
But that means that you also potentially change the design. You're part of that process of designing, as
Yes.
far as I understand. So, because when I look at your buildings and I'm looking at the building behind, I can clearly see like the difference in approach, where traditionally you like building behind is probably developed as a kind of set of let's say tools and elements that would be designed to work together as a one kind of system. And and then looking at your facade, which is, you know, is the texture, you have to think about, it almost looks like the model. Like it looks like you're realizing like an architectural model in a way, in a much bigger scale. So it is it's an entirely different way of thinking, because I would say because the building behind has kind of way of designing in parts and trying to make it work and thinking it all out so it will work at the end. Where in your case, it looks like you can realize the model almost like as one continuous element, and that's of course maybe it's not exactly the case, but I'm just wondering how it changes the design of buildings, the way you work and the way you work with architects.
Yeah, and I think that's a very interesting question, and hard to come up with a short answer, but absolutely. I mean, we're trying to, when we're working in those design assist under those design assist contracts, it's definitely not only the architectural metalwork that we're trying to optimize. And one of the projects I'll get into here in a moment, a little deeper dive on, we'll talk about integration of our architectural metalwork with glazing systems, and combine to, again, try to get to that design intent that the architect had come up with, and kind of how we can work together as a larger project team to, again, make often very small modifications to maybe geometry that can make a very big difference in how well that can be constructed.
But which part of the design stage you come in? Is it like
So for design assist contracts, we might be involved during usually after schematic design, but during but before construction documents are complete. So sometimes we'll be involved earlier, maybe at 50% construction documents, to where there's the program for the building in a lot of cases that's somewhat established. In the case of what's on the screen now, it's a parking garage. It has a certain program. It has to have this many cars. There's some things established about the ventilation. That's where the perforations come into play, obviously allowing ventilation is required.
mm-hmm.
But the facade itself is not finalized. So that's where we would maybe get involved and say, okay, here's a facade system we have that can get to your design. There's some modifications we need. We need, embeds placed in the concrete in these areas, in the slabs. We need extra steel added here and here. We work with the steel designers to optimize that. And then that gets towards where, when the full construction document set comes out, the facade details are in there and they are buildable. So there's not any question that those are buildable. Does that answer your question?
Yeah, I think it definitely does. There's more questions we could ask, but I think maybe we should listen to your second part of the lecture, because then we can understand a bit more how you realize it.
So for the second part, I'm going to focus on the specific project, which is SoFi Stadium in Los Angeles. So this is the stadium for the American football team, well, two football teams, actually, the Chargers and the LA Rams. It's one of the largest stadium projects ever constructed, I believe. Some ludicrous amount of money was spent on this, but This is a rendering, obviously, from early design rendering. HKS was the architect on this project. So when we got involved, and this is another rendering from kind of underneath and showing the what we call the fascia panels here. And so when we got involved in this project, it was roughly at the stage where these renderings have been created. So I'm going to skip a couple pages here and go to, sorry. So zooming in on this on the actual model, what we got to when we were working with the architect was, and the steel designer, was this tri-skin solution. So triangular skins to form this shape with this perforation pattern. So the architect actually done a lot of work coming up with a perforation pattern that they wanted. It's very abstract. I was actually told that it's originally, the idea was the microscopic structure of a ram's horn, which for the Los Angeles Rams. But because the Chargers are also playing there, they can't say that anymore. So it's just abstract. We'll say that for now. So with these tri-skins, and this is just a small section of the building, you can see the perforations, and this is from our Rhino model. There's 37,000 skins that form this structure, or form the facade on this building. One of the huge challenges here is simply the scale of processing 37,000 completely unique skins with unique perforation patterns in the right order, efficiently, and then getting them to the project site again in the right order, efficiently, with the surface finish not affected. Another big challenge was the surface finish itself, which on this project was a white anodized finish, which anodized aluminum is pretty well understood. It's a product available anywhere, but the white anodized, which kind of gives it a more whitish, little bit more iridescent hue, is actually much more difficult to achieve. And so we don't anodize ourselves, but we have an anodizer that we work very closely with. And so we had to go through a process of developing with them exactly what that process would be, and what the quality control would be, to ensure that at the end of the day, we achieved the surface that the architect wanted. Another large challenge with this, and I'm going to skip back a few steps, is so for our machines. So this was largely processed on our punch, which it's a Trump 3000 punch. Typically these punches, the software that they run on, they want something like this. So this is, a single file coming in, and then you were producing 1,000 of that exact same file. So that's how the software typically wants to process that. In this case, we kind of reverse this, where it's not 10,000, but 37,000 unique files, and we want to produce one of each. So there's a huge kind of innovation process in trying to figure out how to do this efficiently, because with the 37,000 unique files, unique pieces of NC code, numerical control code, it would have added something like 30 minutes for programming on each of those files. And that's a lot of time. So it was not doable like that. So we actually, one of our engineers here worked directly with Trump to kind of come to them with this problem. And we were able to develop a software where we could, through Grasshopper, produce code that Trump and their internal engineers could actually use to quickly spit out programs, in seconds, spit out thousands of programs that the punch could then process. So it was a unique workflow that has not been done before, to my knowledge, that we had to develop to be able to efficiently process this project. One of the other things I'll focus on here. So this is just a detail. In this project, there's 37,000 of these triangular skins. So you have a typical detail of what the connection looks like, that's then multiplied many, many, many times. This is, I believe, our final detail for the attachment of these skins. One of the things to note on this is, so let's see, in terms of aluminum. So the skin itself is 5005 alloy, H34 temper, architectural anodized quality aluminum. This piece underneath is 6063 alloy T6 temper extruded aluminum. And then this piece is 5052 H32 temper, so different than H34 temper and different than 5005 alloy aluminum. The expertise required to understand exactly which alloys of aluminum will achieve what we want to at the scale, that's one of the places that we come into play, is being able to guide down to that level the decisions on what alloys are used. And this 5005 AAQ is actually a very unique material. So the architectural anodized quality is a much higher level of surface quality that when you do anodize it, the surface defects will be extremely low and the color will be extremely consistent, which is very difficult to achieve with anodizing. The other thing to note is because of the scale of the project, so we'll go back to high level overview here. So because of the scale of the project, we're ordering ingots of aluminum. I think there were 50 ingots maybe used total on this project. And even with the aluminum supplier controlling the chemistry as best they can, there's still variations within the 5005 alloy that can cause color differences on the anodization. So we had also the expertise of splitting up where the sheets from each ingot were used to not have inconsistent coloration on a specific part of the building. So if you're on two opposite sides of the building, you're obviously not going to be able to see that. Right next to each other, you would. So there were a lot of decisions like that we had to provide our expertise working with the designer to make sure that end of the day we achieved their design intent as best as possible. This is just a workflow of kind of where our, again, very high level of how these tri-skins were processed. This is a section cut through the building. I'll go to some actual photos of this, show a little more. So that's the entire facade that we did, not showing, well, that does show the tri-skins, I guess. That's a picture of a test tri-skin. So that was the smallest ones we got. So again, every one of these is unique, and in certain areas where the geometry is closing off, you got some as small as this, which I would say that's roughly 200 millimeters on a side, that tri-skin. And then that's a picture of a larger full-size one. But one thing to note with this too that we developed with the architect was, you notice these are, the term we use is coined. So it's not just a perforation, but it's actually a punch through that forms this nice smooth edge, which gives a very different look on a small scale than just a pure perforation. This is a picture of some of the code that was given to us actually from HKS, which we worked directly with them to make sure that we could get to this level. So they gave us specific XYZ coordinates of every perforation location on the entire building. So normally we would not get to this level, but we were able to work with them early to optimize this, and it was far more efficient for everybody involved to have them provide us with this data. Another thing to note, this is a layout of a lot of this large number of the triangular skins. If you note the material, the sheets that these are laid out on, this is a nesting study. The sheets are not rectangular. They're actually cut into a parallelogram shape. So this is where we can, if we get involved early, we can optimize the sheet ordering to actually minimize fall off, minimize waste of material by pre-nesting. And all these actually vary in size, but we were able to pre-nest and order, I think it was 3 or 4 different parallelogram sizes specifically to minimize waste, which on a project of this scale saves tons of aluminum over time. That's kind of a close view of the actual final file, with the kind of dashed line perimeter being the sheet. And then you can obviously see the material, the actual skins. One thing to note here too, we developed a dot code. So this down here is a dot code that can be read to help track these skins through every part of the process. So because they're actually cut, then in the flat shipped to the anodizer, then shipped back to us to form, and then shipped to the field. And so it's very critical to track the location of every skin where it was at any given moment. Excuse me. This is just an illustration of running through the program to nest all the skins. Excuse me. So this is our Trump 3000 punch. So all 37,000 skins went through this machine. It took about a year and a half total of 2 shifts a day, 5 days a week running on this machine. I don't know how well that video came through, but this is the tracking software we use. It was reading those dot codes. Then we could pull up this Excel spreadsheet at any given moment, and it was kept up to date about where any given skin was at that moment in time. Close up of the cut panels. This is our brake. We actually bought a specific brake for this project to form these skins because we had a specific size. I think the brake process for all 3 sides of this is something like under a minute to break each one, even though they're done manually. High level view of the project. So just for some scale on this, that's about 500 meters from end to end. And this is obviously a while ago. The project's finished now, but kind of showing the project site. And then if you notice down here at the bottom, we're going to zoom in a bit and then zoom in a bit more. And so this area right here is this large field. This project is kilometers across, the project site was. And all of these boxes actually contain our tri-skins. This is those skins being assembled onto a space frame. So we worked with another company who is more of an expert on steel construction, on space frame construction. And we located the node points of the tri-skins, worked with them, and made sure that our models obviously collaborated to make sure those node points were exactly where they're supposed to be. We had 0 issues on 37,000 skins for locating exactly where these node points were on the space frames. And so really, when you get to this is an extremely efficient system for supporting this facade. So space frame steel, it's well understood. It's a relatively optimized system. And then our aluminum panels on the outside. And one thing to note as well, a lot of these connections are up on the roof where they're not visible, but some of them, such as these points where this would come down to, are actually quite close to where a person could walk up to within, 10 meters of that. So the way those details looked, even though it was extremely large scale, the detail still had to look nice. So making sure this was tight with sharp points was still a critical thing from a design aspect. And this is just some installation of some of the mega panels. So they this is a decent picture. So this crane right here lifted each of these panels, the space frame clad in our skins up onto the building one at a time. These clad frames weighed up to 100 tons each. So this is, I believe, the largest crane available in the United States, the largest crawler crane. was needed to lift these. And the installation was not done by Zahner. So the steel subcontractor that built the space frames did the installation. And you can see in the background the scale of these cranes. And again, this point, you can see how it almost looks like it's buried in the dirt. I hope that didn't end up quite that way, but it gets very close to the ground, the details. And you can see the perforation pattern, how that comes through. And, going back to that rendering, it matches the rendering. The rendering looks like what the final building looks like. So that's what I had on SoFi Stadium.
Great. This is very impressive to see, I have to say. It's very hard to swallow. It's a bit like what Jonas was doing design-wise, testing out the sheer kind of scale, possibility, like how far can you go in scale? And this is obviously, what makes this very special is this enormous scale and enormous, let's say, effect any time would have on designing, producing, creating this algorithm for every panel and so forth. So I mean, I calculated like from what you said, if you use half an hour to do the algorithm per panel, you would be around 2,300 days, which is like 6.5 years just to calculate the algorithms, which
Yes.
sounds, I mean, if you take it up, it's probably what in the history, how these buildings have evolved. Like some buildings took much more than that. I mean, just thinking of Sagrada Familia in Barcelona, but I think the so one thing is to see the kind of amazing efficiency in terms of time, and there I agree, it would be impossible to realize if you would all do it by hand. The only question I have is, how do you install them? Like, I mean, I see, well, let's say from my experience from projects where we had just 24 different nodal points with different geometries in a structure. To install those, there was a temporary building would be built up several times. It was like a small theater. It took like several hours at the beginning, and they brought it down to 2 hours. The main problem was to find the places for those nodal points. In your case, you have 37,000 panels. They're all different. How do you install them, and how do you find the right place for them to put them in?
And that's where the early collaboration with the installer, let me go back to this photo. So we worked with them early on sequencing. So the way that they were going to break up their space frames. So, whatever number space frame this is, and then how they were going to install them, like in the rows, and then working all the way back up to our programming step, we're releasing machine files in the order that's, all the way downstream the installer wants in the field. So from the machine file release, it has to get punched, go for it to get anodized, get formed, and shipped to the site. But during that time, it follows that order that was established for the installer. So that when, this crew in the field opens up a crate, the first panel they see, the first skin they see is the one they need. So the logistics of that are extremely critical. If you get it wrong, it can make a project like this go.
No, that's a mess.
Far less. Yes.
So then you
and there's no way. No. If a panel didn't have a name on it, you would never know where it goes. No. So it's impossible.
Yeah.
So what, that adds another question, like how many times did it go wrong?
On this one, so we during the process, I think there were maybe 20 panels that were misplaced over time. And this was, it usually happened when we shipped them to the anodizer because they had to be dunked in an anodization tank. And then there were some missing things there, but it was extremely minimal. And then we were easily able to identify the panels missing, quickly refabricate those specific panels, and then ship them to the field. And in some cases they did, you can see from, well, actually any of these photos, there were these zipper sections, as we called them, that were the joints between the large mega panels. So they were going to have to go back anyway and install specific panels in the air. So even if some were missing, they could still lift a full panel or a full mega panel and then go back and replace a specific one that was missing.
And is it that if you, let's say, one of the panels get damaged in the future, they would give you a call and you would say, they would give you a number and you could reproduce it?
Yes.
Are they all signed? Do you know exactly which panel sits
Yes.
oppositely, and you just call
Yep.
back?
So they would just have to read the panel number on there, and we could reproduce it. The issue being the anodization, the color might be a little bit off. That's the thing that you can never quite reproduce perfectly, but we would do our best to reproduce that. Any other questions on that?
Jim, you've I mean, maybe it was before your time at Zahner's, but Zahner's built the De Young Museum by Herzog de Meuron. And how has the process changed, looking at the perforated sheets and the coating? Because then with the De Young Museum, you've got perforated and embossed sheets, and they're like also like zillions of different patterns. How have you like evolved the process?
Yeah, so interestingly with De Young, we were using, I believe we used AutoCAD and a VBA script in AutoCAD to produce the perforation files for all of those.
Yeah.
And what's kind of funny about that is there was no visual check at the end of it. It was all in the code. So it produced in C code without a visual check. It worked out, but it was not a robust process. It was an early iteration of that process. So that's evolved a lot over time to try to optimize.
Great. So maybe I would love to see the next part of your
or a question from the audience.
Yes, any questions, please?
I'm offering a free beer for a question. Next time I come to Stuttgart or you come to my place, I'll offer you the beer. A large one.
And we can always come back at the end and ask other questions about this too. So. Okay, so this project, which again, I think I mentioned this earlier, but we're still under a non-disclosure agreement on this project. Not complete yet, so not going to say the name of the client. You can interpret from the location and the architects what this might be, but we're going to talk about Zahner's scope and our design assist process on this project. So, and we'll call it Bayview. So overall view of the project, and zooming in, this is an early rendering, and Zahner's scope on this is actually all the edges. So the edges of these kind of canopy sections. So kind of what's outlined here, and actually it's all the edges. So even the ones that are not dashed in green, but that was Zahner's scope. And the key there is that, you know, the visual, what catches your eye is the edge. So, and these are smooth sweeping curves. So achieving that out of metal in a way that's going to be robust, hold up over time, and actually was installable was very challenging. So this was an early design prototype we built. One of the most challenging things about this is the node points where the different edges come together, making sure that those meet up in as clean of a way as possible. So we built this early mock-up to kind of test what the skins would have to do at those points to come together cleanly. We actually did this in, I believe, 2015. So it's been 6 years ago. And again, project should be complete this year. So it's been a relatively long process. And we were involved early on in design discussions with the architects. Again, this is Heatherwick and Bjarke Ingels for the design architects of the project. And Adamson is the architect of record. So one of the things that we had to work on early is these, what we call bullnose edges. So in the architect's model, they varied because as they curved, they were not a constant radius. As far as for forming, that would create a huge challenge. What we wanted to try to get to is where we could use a constant radius die and a break to form that edge, but it would have to be cylindrical. You obviously you can't curve metal. Well, you can, but at scale, you can't really curve metal that's also curved in both directions. And one thing to note about that process is that we'll often mill dies out of aluminum first to test shapes. And then if the shape works, for longevity, we'll then have a tool maker actually make that out of steel. So we do a lot of internal prototyping because it's easy to mill aluminum. Aluminum won't hold up over time on these projects, but it allows us to do a lot of prototyping internally prior to involving a tool maker. This is, again, that same mock-up I was showing you actually built. And this is Bill Zahner, the owner of the company up here. He installs all of our projects personally. So always up there in the basket.
Cool.
Really. So similar to what I showed on the SoFi Stadium, we had a pretty extremely in-depth nesting process on our panels, on the substructure that we formed for these panels to make sure that we're, again, optimizing sheet size and staying within structural requirements. What you're seeing here is an unfolded version of the substructure that forms the support for the actual stainless steel skin. This is from our probably our Rhino model of this project, showing all those along one edge above some clear story windows. So that's just one edge of the canopy. And so you can see that's kind of an unfolded shape of these folded up shapes. We often do process like this where, again, we're doing layout of all the shapes for one row of panels for nesting purposes, to do quality control checks on, hole diameters, dimensions, all kinds of things like that, because again, every panel is unique. And you can see how they vary slightly over the facade, but they are all unique. That's just a pile of those same parts built out. So one of the challenges with this is, and I'm going to go back a couple steps to this. So with all these panels, and so we had to panelize this system. So our point is to always keep as much of the work that requires high accuracy in our shop, so we can control it in the shop. And then when it gets to the field, there's minimal adjustment required. So we worked with the curtain wall manufacturer of these clear story curtain wall panels to basically align our panel joints with their glazing unit joints. One of the things with this is those glazing unit, the joints are all true vertical, whereas these sweeping curves are all different angles. So what you end up getting is a situation where all of your formed panels are actually racked. So they're not rectangular, they're kind of racked at an angle into a sort of parallelogram type shape if you're looking straight down on it. And with them all being unique, we had to come up with a custom system to lay out every one of those panels, check the dimensions, lock them in before we made final attachment of the anchors, which are these aluminum pieces here, and the stainless steel skin. So this is the modeled version, and that's the version actually in process. And we did have these are all mechanically fastened skins on the top and bottom, but then we used a structural silicone adhesive, which is the same type of adhesives they would use in structural silicone glazing, to attach stiffeners, essentially, to keep the panels flat. This required a very large amount of testing to make that process work correctly. This is a similar panel on the same project. Is actually the perimeter panels. They're not the ones above the glass, but around the very perimeter of the building. So because of the need to have the adhesive cure without dead loading the skin against it, we had to build these rotisserie jigs to basically allow us to put it in this orientation to allow the adhesive to cure for this skin. And then you would roll it when you apply the adhesive for the next skin down below. So this is a photo of the combined hour unit on top that's attached on the ground to the glazing unit and then lifted as one onto the building. Won't go into this too much. Not going to go into too much detail. Save a little time. But one of the keys with this is that we, excuse me, had a process of, there's a survey of the steel anchors that was fed back to Zahner. The structural steel engineer for the building, Thornton Tomasetti, provided us with pre-calculated deflection of the steel, because when we were installing these units, the overall the full roof was not installed, so the steel was known that it was going to deflect further after installation, and we were actually able to account for that with our anchor adjustments when we installed these, so that once the full roof is loaded on and the steel deflects, the panels will be aligned. So picture on the ground of some of our units above the glazing. Units.
So we're missing some sound.
Department is providing this dimension.
Yeah.
Can you hear me? Okay. So after all that work, what that gets us to is a very smooth and continuous edge with minimal joint. There's going to be a joint, and it's meant to align with the joint in the glazing units, but try to minimize that. And you get a really nice, I've always liked this photo because it shows those very smooth edges that our panels ended up creating. Zoomed out view of one of the buildings. So you can see this is the what we call the clear story units that sit above the clear story glazing. And then these are our large perimeter panels that are essentially establishing that same bullnose edge. And one thing to note, you can't really see it well in these photos, but all the points between, so on this roof section, are all covered in photovoltaic panels. So this building is meant to produce, I believe, more electricity from photovoltaics than it consumes. So again, you look forward to being able to, integrate photovoltaics directly into our systems at some point. But in this case, we're providing kind of the aesthetic edge, framing out all the photovoltaic panels in the middle. This is a recent photo of 3 of the 4 buildings. And in total, there were 2,000 unique panels on the project. And it really went extremely well. So we're almost done with installation, and it's been a very smooth process. But going way back, it required a lot of coordination between Zahner as the architectural metal supplier, Benson was the glazing unit fabricator and installer, the design architects. There's a lot of early input to how we could optimize those shapes. And again, in the end, I think this photo speaks best to our product on how smooth that we were able to get with that bullnose.
Fantastic. And I mean, I have like my question is on this. You seem to be getting involved. I mean, now it's very clear, very much deeply into the design process. So not just kind of helping, or let's say not helping, but designing with the engineers and architects to find the right geometry, but also to actually. It looks like, and maybe you have to correct me, but it looks like there's a lot of your time is on the design of the technical, details and how you actually make it work, so it fits into the production process that your tools can provide. I mean, it's something that, of course, you would have with a lot of contractors, that you would have to design it and develop drawings to make it happen. But when you look at, for example, membrane construction, you have most of the, or maybe now it's kind of evening out, but it used to be that most of the cost of the membranes would be in designing the membrane and kind of creating that kind of pattern that's required and making sure it's all correct and detailed. But and the actual fabrication is much quicker. And so it looks to me, and I wonder how much percentage you would say does the design take, and how much you actually use to produce it. Because I can see like a lot of detail goes into creating that edge, not with a kind of, because everything seems to be unique. You have to redevelop it. You can't just rely on, let's say, a norm system like, let's say, bricklayers would use, but you actually have to create a completely new system for your own design in a way.
Yeah, and I would say that one of the key things with something like this, the architect is defining that surface that they want to see. They didn't have it cut up into the panels or know exactly how it was going to be created, and it was a non-constant radius bullnose. So starting with that, we know that's the architect's design intent. That's what the designer wants to see. Now we start integrating concepts as far apart as shipping and structural engineering requirements and installation requirements, material sheet sizes. It's obviously, stainless steel, you can get 1 meter sheet, you can get a little bit bigger than that, but you can't get a 5 meter wide sheet. It can't be done. So trying to find, okay, how do we develop a process that can best get the architect's design fabricated? So and like the tables we developed and the jig systems and the installation systems are all unique to this project. We've done stuff that's similar in the past, but we're always refining, updating those processes to work better on the next project and push the limit of what's possible. And really, that's something that as a company, we don't want to get to where we're just doing what has worked for 20 years. It's easy, but it's not going to quite achieve what the architect wants to. We like when architects approach us with new problems, and then we can design, hopefully refine some existing workflows and systems and maybe design new ones that will make that possible. So really,
I
there's a
think this
lot of
is
time
a
spent figuring out what that unit is, like a single unit, and testing it on the most extreme cases. And then really when it comes down to actual production work, we build out templates, and I haven't talked too much about software, but for this project, we used CATIA extensively, or 3DX as they call it, but to build out a template in CATIA that we then were able to instantiate over the entire building and make those 2,000 unique units.
it's like interesting. It's almost, you know, like what you said there. You are interested in architects developing a problem that you can solve. Like it's actually very different approach, and because I think that you part of what you do seems to be that you're a problem solver. Like you rely on the problems to be there. Otherwise, you can't do with your expertise. And I wonder, like, how many designers do you have? Like, how many? I'm looking at your office behind you and just thinking, how many designers do actually sit there, and how many are working on the construction site? Do you have a?
Yeah, we have roughly 20 to 25 people in project engineering. And then there's a lot of basically in this office behind me. And then we have project management and other support staff throughout the building, in this building and our other one. So yeah, so it's about 25 people that are working on various aspects of design and production engineering on projects, because they tie closely together.
So you become more like almost like a design office.
Yeah, to some degree. I mean, and an interesting thing about this building. So underneath the photovoltaic panels, what you see here are actually the halters for a BMO roof system is going on this. So just the formed 100 and, in this case, I think they're maybe 40 meters at the longest, formed roof panels that are just formed sheet metal. In theory, Zahner could do that work, but it's not, the problem's been solved, and it's not anything particularly unique. So, that's something where another company is going to be able to do that more efficiently. So that's we specialize in the stuff that's a little more on the cutting edge. That's what we want to do, and really the people that work here want to do that kind of work. We want to problem solve the problems that haven't necessarily been solved in the past.
Fantastic. I mean, maybe we should. I'm aware of time, and I'm aware of your voice also, Jim, because
Yes,
I can hear. I know you have a bit of a cold, and I just worried that we won't hear you after a while. But I just wonder if we can just have some last questions from the audience. Some, feedback or questions would be really nice to have. So if there's someone in the audience who wants to ask, this is the chance basically to ask questions. Is there someone? Just speak up. I mean, don't have to put it in the chat. You just speak up.
The beer offer still stands, I believe. So
Of course. I find this hugely interesting, Jim. Thanks so much for sharing these projects with us. And you've been always so innovative as a company, like developing your own apps. You have like this survey link, which just arrived, I think, like yesterday, again as a notice, and so that you can track with an app the locations on the building site, and you have, I don't know how many patterns running with special profiles and cladding systems. And I don't know if there's any other company on the planet as innovative as you are. So I'm a huge fan of yours. And
thank you.
Yeah, I think it's
again, some masterpieces you've showed and shared.
Yes, so also from my side, I mean, I think it is amazing that you know the work you're producing, and I'm very happy that you showed also the most recent work, which I know is always difficult, you know, with copyrights and, you know, I'm sure we can go into Google and search for this building somewhere. But I think it's we'll find it, you know, but I think it's super interesting to see because it kind of the way you're producing, you know, it opens up a lot of possibilities. And I think for architects, especially, I think there's lots of yeah, new possibilities how to make architecture, and but also it's important for us to understand, you know, how this system is actually part of the design process that we're developing as architects. So they, you know, I think it's a different kind of questions the classical conventional you know construction process, or let's say design to construction process. And I think that's what's so exciting about the work that you've shown, that you can see that, you know, if we want to do these kind of buildings, if we want to, you know, kind of push the boundaries of architecture, I think that we'll have to work together between, you know, the people who produce this and the people who design this, and, you know, get them together at the very early stage and starting to develop it together. I think that's the main, or one of the big messages that I take away from today. And it's really beautiful to see.
A dialogue.
Yeah.
Yes. So I think we're come to an end. And I'd like to thank you very much, Jim, for showing all this. And even though you had a cold, and I'm very happy that your voice is still standing. So thank you very much for showing all your work, and fantastic to have you. I hope we can get you to Stuttgart one day and show you what we're trying to do in our research, and maybe there's some ways of cooperating, or at least exchanging ideas. So thank you very much.
That would be great.
Thank you also. I mean, also maybe you want to join tomorrow. It's also thank you very much for the audience who was there. Tomorrow there will be another talk by Arthur Manamani, who's a London-based architect who integrated the digital fabrication into his design process as well, who is also developing the most well-known project he did is a installation for the Burning Man Festival called Galaxia. And it's all, even though constructed by hand, is all developed digitally and fabricated digitally as well. So I think it's also very interesting lecture to hear. So now I can just wish you good night, and for those who are watching football, good luck with the with the scores tonight. And yes, thank you very much, Jim, for coming and showing all your work. Fantastic.
Thank you for having me. It was a pleasure to be here.
Thank you, Jim. Many greetings to Bill and Gary and your wife.
Yes, will do. Thank you.
Talk to you soon.
Thank you very much.
Thank you.
Bye.